So students, allow me start officially the lesson for today. And I say that we'll be looking at the self-ionization of water. Then we also look at pH of acids, bases, and how we can calculate the pH. Now, what I'm showing here now is the dissociation of water, whereby you have a water molecule breaking down to give you a hydronium ion, and another water molecule is also breaking down to give you hydrogen and some hydroxyl ion. So when you balance this equation, you realize that we do have two water molecules that are dissociating, and in the process, you have the formation of the hydronium ion and hydroxyl ion. And remember, I said that this hydronium ion is just acid in water. And another way of looking at it is looking at it in terms of whether it is a conjugate base or a conjugate acid. And I was able to explain that in our previous lesson, that this hydronium ion here becomes the conjugate acid because it is formed from water after water has actually gained a hydrogen ion. So this is the process that takes place. And we can talk about what we call the dissociation constant, or the equilibrium constant for the product. Now, if I take you back to the previous slide, now here we have a water molecule. Again, allow me pick my pen and admit some students. They are admitted. So this is a water. This is a water molecule, and this hydronium. So if we were to write it as a simple chemical equation, then we would simply write, I would actually, although this is our last class students, it is important that students, all the students join the class on time, because we are available to admit you before the start of the lesson. It is not very good for me to punctuate my explanations so that I can admit students to the lesson. So in future, please be joining the class on time, just to avoid these unnecessary disruptions. So I can write this one as 2H2O, which is giving us the hydronium ion plus the hydroxyl ion. Normally, we write what we call the constants for a particular chemical reaction. And this comes from something that we call the reaction quotient. And therefore, if you look at what is being shown in the second slide here, the equilibrium constant here, you can see we have Kw is equal to, now when you see H30, the hydronium ion in square brackets, that in chemistry means the concentration. So we have something like Kw is equal to the concentration of the hydronium ion multiplied by the concentration of the hydroxyl ion. Where is this one coming from? If I explain using this equation that I have already written here, then we can say that, again, my pen has gotten lost. Allow me to pick it. I'm still looking for my pen. Thank you. That's there it is. So when we are calculating this constant, we actually look at what we call the reaction quotient. And what is a reaction quotient? A reaction quotient is obtained from the concentration of the products divided by the concentration of the reactants. And therefore we can write K is equal to the product of the concentration of the products. So these are the products here. So we take their concentrations and multiply. And therefore here we will have there's a student joining, so allow me again admit them. So this is equal to, I put a square bracket. This square bracket means the concentration. So I put the hydronium ion. Then I multiply by the concentration of the other product, which is the hydroxyl ion. And then we divide by the product of the concentration of the reactants. So the reactants here, we only have water, and therefore we put into brackets water, H2O, we put that one. And something I want to tell you here is, now in this equation I've written here, there's something we call the stoichiometric coefficients. These are the coefficients that we put for purposes of balancing the chemical equation. For example, for water, the stoichiometric coefficient is 2. For hydronium, the stoichiometric coefficient here is 1. And for the hydroxyl ion, the stoichiometric coefficient here is 1. Now, these stoichiometric coefficients, when you are writing the dissociation constant, they become powers, and therefore, the power here is 1. The power here is 1 because the stoichiometric coefficients of these species are 1 each, and the power down here is 2. Now, the question is, do you need to show the power if it is 1 here? The answer is no. And for that reason, we can do away with this 1 here. But these 2 has to remain because it is significant in this particular equation. Now, we also know that in the autoionization of water, a very small percentage of it is going to ionize at every instant. Actually, we say that 100 million, 1 out of every 100 million molecules of water is going to auto-ionize, is going to undergo self-ionization. Now, if we talk about 1 out of 100 million, that is 10 to power 8. And say that these are the only molecules which will auto-ionize at every instant, then you will realize that it's like nothing is auto-ionizing. Nothing is undergoing self-ionization. And for this reason, we say that statistically, the concentration of water is going to remain essentially the same. So that the initial concentration of water here is going to remain the same throughout because only very little of it, only 1 out of 100 million will undergo the self-ionization at every given instant. So we say that this one is a constant. The initial concentration of water is a constant. Now, because K is a constant, we go ahead and multiply these 2 constants by bringing the like terms together. So we actually have K into the concentration of water into power 2. So here you will realize that this is the new constant. So when you multiply a constant by a constant, what do you get? You get a constant. And that is why in the equation that we have shown, we have written KW. This K here is the K that I've shown here, and the W here is this water that I have multiplied with. And that is why in this equation here, let me do away with the drawings. Now, in this equation here, sorry, we have written Kw is equal to the concentration of hydronium ion multiplied by the concentration of hydroxyl ion. And at 25 degrees Celsius, then this ion product of water is equal to 10 to power -4. And if I were to give the units, again, allow me look for my pen. This pen of mine is disappearing. Just bear with me, students. So this is a 10 to power -14 mole squared per liter squared. Those are the units of this ion product. And where is that one coming from? It is coming from this product here. Remember this concentration, and this is moles per liter. This is also moles per liter. And when you multiply the two, you get moles squared per liter squared. So this is what you get. Now, this value changes depending on the temperature. If you change the temperature, the value is also going to change. So because it is a function of temperature. So we are saying that as the temperature increases, this value of Kw also increases. Now, when we talk about the concentration of the hydronium ion and the concentration of the hydroxyl ion, it is those respective concentrations that determine whether a solution is basic, acidic, or neutral. And that's why we are saying that the concentration of hydronium or hydroxide in a solution of strong acid or base is related to the stoichiometry of that particular acid or the base. And for example, if you look at this, calculate the concentrations of hydronium ion and hydroxide ion at 25 degrees Celsius in these two solutions. Let me explain what is happening here. Now, the first one is nitric acid. And nitric acid, we know, is a strong acid. And a strong acid is going to fully dissociate in water. So you have HNO3, which is going to dissociate. And once it dissociates, it will give you hydrogen ions plus, let me put plus appropriate, plus nitrate ions. That is what happens when this nitric acid dissociates. So the question that we are supposed to ask ourselves is, now, what is the reactive mole ratio? Let me use my pen to write it. It's better. So when you have HNO3, then being a strong acid is going to dissociate fully. This is going to give you hydrogen ions plus nitrate ions. What is the reactive mole ratio? Is this equation balanced? Yes, you realize that the equation is balanced as written. So 1 mole of the nitric acid is going to give us 1 mole of the protons, or 1 mole of the hydrogen ions, and 1 mole of the nitrate ions. So if we have 0.15 moles, so if you have 0.15 here, it means that we are going to get 0 0.15 and 0.15. Now, calculate the concentrations of hydronium ion and hydroxide ion. You know, the hydronium ion, which we write as H3O plus, is actually the concentration of the acid here. And why am I saying so? For this nitric acid to be aqueous, actually what we have is I'm admitting somebody. What we have is HNO3 plus water. Or what do you dissolve this nitric acid in when you're making dilutions in your labs?
Water.
You use water. That is the water I've written here. And that's why actually you are going to get H3O plus NO3 like that. So again, the reactive mole ratio here is 1:1. And what we are interested in these calculations are the concentration of this hydronium ion, the concentration of this hydronium ion, and the concentration of hydroxyl ion. Okay? So if we are given 0.1 mole of nitric acid, then the concentration of the hydronium ion is going to be 0.15 molar. Now the question is, calculate the concentrations of hydronium and hydroxide ion. So whenever you get the concentration of the hydronium ion, you can get the concentration of the hydroxide ion, because we have seen that Kw is equal to the product of H3O plus into the concentration of the hydroxyl ion, like that. And this is supposed to be 10 to power minus 14. Okay? It is supposed to be 10 to power minus 14 at 25 degrees Celsius. At 25 degrees Celsius. Therefore, it means that if you have already established the concentration of the hydronium ion, which is 0.15, then you divide both sides by 0.15 so that you can get the concentration of the hydroxyl ion. So for every question here, you can get both the concentrations of the hydronium ion and the concentration of the hydroxyl ion. For example, here we are saying that the concentration of the hydronium ion, as I have explained, concentration, remember we are writing like this. This is equal to 0.15 molar. Then the concentration of the hydroxyl ion, this one, is equal to 10 to power minus 14. This is m squared. Mole squared per liter squared is the same as molar squared, divided by 0.15 molar. Anybody wants to ask where I'm getting 0.15 molar from?
I want to ask why you're dividing.
Why I'm dividing? It is because we have said that Kw is equal to the concentration of the hydronium ion You remember this one?
Yeah.
And this is equal to what? 10 for negative
14.
14 m squared. You remember that?
Yes.
Now, from this, we have been able to calculate and find that the concentration of the hydronium ion is 0.15, isn't it?
Yes.
Let me pick a call. Let me pick a call. Just one moment. Your Excellency, how are you? Hello. Your Excellency, are you able to talk? Yes. Please get well soon. I'll call you. I'll call you, please. Sorry, students. Can I continue explaining that?
Yes.
So the ion product of water is what we have given here. Can you see this? And I have explained that when this nitric acid dissociates, I have explained the equations. It is going to give us 0.15 molar of this hydronium ion, isn't it? So for us to get the concentration of the hydroxide ion, we simply say 0.15 multiplied by the concentration of the hydroxyl ion is equal to 10 to power minus 14 m squared. So the question now is, how do we get the concentration of this? That's why we are dividing both sides by 0.15 molar. Is that clear from the student who asked?
Yes, yes. Thank you.
There was a question, there was another hand raised. Can we go back to that? I saw another hand. Yes.
It was Nicholas.
Yes, Nicholas.
Okay. I actually got the answer. Like, I wanted to ask, because the mole ratio was 1, that's why we are getting the same concentration of hydronium ion.
Yes, the reactive mole ratio is 1 to 1.
Thank you.
Okay, so let me explain question number 2. Here you have calcium hydroxide. So you have calcium hydroxide and this is dissociating in water to give you calcium 2 plus 2 hydroxyl ions. That equation is balanced, isn't it?
Yes.
And I said we are only interested in the hydronium ions and the hydroxyl ion. And you can see the hydroxyl ion here is given. So 1 mole of the calcium hydroxide is going to give us 2 moles of the hydroxyl ions, isn't it?
Yes.
So the reactive mole ratio is 1 to 2. Now, what you are given here is 0.01. So if this is 0.01, this 0 here is not of any significance to us. If this 0.01 molar, the question is how many moles or what would be the concentration of the hydroxyl ion on this side?
You multiply by 2.
So you get what?
0.02.
This is going to be 0.02. So that is going to be the concentration of the hydroxyl ions. So can we also get the concentration of hydronium ions?
Yes.
How do we do that?
We divide by the constant. Constant divided by the number of moles we calculated.
Which constant is that?
The water,
The KW.
ionization one of water. So
Hmm?
I think
So we take 10 to power minus 14, isn't it?
yeah.
M squared, molar squared, and we divide by what?
0.02.
Very good, 0.02. And the answer that you get will be equal to the concentration of what? The hydronium,
Oxide. Hydronium. Sorry.
the hydronium ion. Any question on this?
So are we leaving it like that, or we divide and write the final answer?
You write the final answer. Write the final answer. Because what we need is the final answer. Is that okay?
Okay. Yes.
Okay. Okay, thank you. So that is what is being explained here. You can see that's what is being explained here. The same thing is being explained here when we are taking 10 to the power minus 14. That's explained there. So I can move to the next slide and say this. Now, we can characterize solutions as either acidic or a basic or a neutral. And if we are looking at 25 degrees Celsius, then when an acidic solution is talked about, then the concentration of the hydronium ion must be greater than 10 to the power minus 7. And where does that one come from? I will explain. Now, when we talk about a neutral solution, let me begin here. Begin with the neutral solution. When you talk about the neutral solution, a neutral solution is when the concentration of the hydroxyl ion and the concentration of the hydronium ion are exactly the same. And how are they the same? They are the same when you look at that ion product. Let me go back to that ion product. When you have this H3O into H plus, and we know that this product is 10 to the power minus 14 at m squared at 25 degrees Celsius. Now, when that solution is neutral, then the concentration of this one is equal to the concentration of the other. So that they may cancel completely, so that in that particular solution, we do not have any base, we do not have any acid. Both of them are equal so that they completely react with one another to give us a neutral solution. Now, if that is true, then we say that these two concentrations are the same. And if these two concentrations are the same in this particular equation, you can write one in terms of the other. Because if this one, H3O, is equal to H plus, mean OH minus, not plus. If this is true, then mathematically here we can express one in terms of the other. It's supposed to be like this. Do you agree with me?
Yes.
Yes.
So supposing that we express these two in terms of the hydroxyl ion, so we can now write OH minus multiplied by OH minus becomes OH squared, isn't it? Is equal to 10 to the power minus 14 m squared. So for us to get the concentration of the hydroxyl ions, we divide, or we get the square root of both sides. So we get the square root here, and we get the square root here. And once we do that, we're going to get this is equal to 10 to the power negative 7 molar. Yes.
Have you really
Pardon?
like look for square root or you're divided by 2?
We are not dividing by 2, we are getting the square root.
Okay. Oh, yeah.
Can I explain why we are doing that?
Yes.
We are getting the square root because look, what we have here is the square of the hydroxyl ion. So for us to get the concentration of the hydroxyl ion, for us to do away with this square, we get the square root mathematically. That's how it's supposed to be. So we are not dividing by 2. Is it clear?
Yes.
Is there any student who wants me to explain further?
Yes, please. I did not understand how you got the square in the first place.
Okay. Let me explain. We say that confirm whether you are familiar with the equation I'm writing here. This equation here into OH is equal to 10 to power negative 14 m squared. Are you familiar with that equation?
Yes.
Then I have gone ahead and said that for a neutral solution, I said I want to begin by explaining this. For a neutral solution, then we have these two are the same, are equal. The hydronium ion, this one is equal to, exactly equal to the hydroxyl ion. Are we together there?
Yes.
Now, if they are equal, then in this particular equation, I can say if this hydronium here is equal to the hydroxyl ion, instead of writing the hydronium, I can write what? Hydroxyl ion. Because in a neutral solution, they are equal, isn't it?
Yeah.
So if I write so, then it means that I am taking a hydroxyl ion multiplied by hydroxyl ion. These are concentrations. And this is what is giving me the concentration of hydroxyl ion to power 2. That is where the square was coming from.
Okay.
Is it explained?
Yes.
And then we say that this is equal to 10 to power negative 14 m squared. What are we interested in? We are not interested in the concentration of the hydroxyl ion squared. We are interested in the concentration of the hydroxyl ion. So what we do, we actually get the square root. If I can use another language, we raise it by power a half. Cindy, power half is getting the square root.
Yeah.
We raise by power a half here, and we also raise this one by power a half.
Go.
So when we raise this one by power half, we are simply multiplying the indices. We are multiplying the powers. So you get 2 multiplied by a half, you get 1, isn't it?
Yes.
So that is how you are getting the hydroxyl ion concentration is equal to, when you raise to power half, this one is divided by 2, isn't it?
Yeah.
So you get 10 for negative 7. Then molar, its power is also divided by 2. You get to power 1, which is supposed to be like this. That's why we are saying that in a neutral solution, the concentration of the hydroxyl ion is equal to the concentration of the hydronium ion, H3O plus, and this is equal to 10 to power 7, this one, the one which is shown here. Is it clear?
Yes.
Now, there is a student, I think, called Grace, who had raised a hand. Please ask your question. Grace? I think I saw somebody by the name Grace.
Oh, so you had written something wrongly, but it's okay. You had
Where
written,
is it?
It was before you started explaining when you did the square root.
Yeah.
I was to ask, if you do the square root of 10 power negative 14, will it become 10 power negative 7 or 1 power negative 7?
It will become 10 to power negative 7.
Okay.
Yes. What we divide here by 2 are the powers. This power here. Are you answered?
Yes.
Very good. So if this is true, in a neutral solution, this concentration is equal to 10 to power minus 7, also equal to the concentration of the hydroxyl ion. Like I saw a student joining, let me admit them. So if that is true, then now what you increase beyond this concentration will determine whether that solution is going to be acidic or basic. For example, if a solution is neutral and you increase the concentration of the hydronium, then that's why we are saying that when it is greater than 10 to power minus 7, then you are going to get an acidic solution. And if this is less, then you are going to get a basic solution. In fact, when you look at, you can start with, is that another student who has joined? Okay, let me admit them. So it depends on what you increase beyond 10 to power, 10 to power minus 7. So when you increase the concentration of the hydronium, then you are going to get what? You're going to get an acid. And when you reduce that particular concentration, you're going to get a base, because if it is at 25 degrees Celsius, as one increases, the other one must decrease, so that the ion product is equal to 10 to power minus 14. For example, if I can come up with a table here, just a small table, and this is a hydroxyl ion concentration minus, and this is the hydronium ion H3O plus. Now, if this one is 0, if this one is 0, then the concentration of this one must be 10 to power minus 14. So that actually you cannot have a 0. Is when this is a 10 to power minus 1, or if this is 10 to power 0, 10 to power 0 actually is 1. If this is 10 to power 0, then this one must be 10 to power minus 14. Now, if this is 10 to power minus 1, this one must be 10 to power minus 13. If this is 10 to power minus 2, this one must be 10 to power minus 12. Can you see a trend here?
Yes.
So that each time you get the product of the two, you get what? 10 to power minus 14. Let me continue here again. And here I have, let me pick another color, just for illustration purposes. Let me admit somebody was joined. Now, if we continue with this one being the hydroxyl ion, and this one being the hydronium ion, we had gone up to 10 to power 2. So if this is 10 to power negative 3, this one has to be 10 to power negative 11. If this is 10 to power negative 4, this one has to be 10 to power negative 10. So it will continue so that when you have this is 10 to power negative 7, this one must be 10 to power negative 7. And this is when we say that the solution is what? Neutral.
Neutral.
Okay. Now beyond this one will be 10 to power negative 8, while this one becomes now 10 to power negative 6. So now the trend will continue shifting. There is a hand raised by, no, there's no hand here. Is there a hand raised?
Yes.
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 I wanted to
Asna,
ask.
yes, yes.
Yes, because it's a bit confusing. For when you say for acidic more than, does it mean the power is increasing or decreasing? Is it becoming -6 like that?
Okay, let me draw a table here, students. Then we can discuss. Let me just do a table now.
Okay.
Let me just do a table here, so that I can explain what that student is asking. So I'm drawing a table here. Let me just make some adjustments to the table. So that we have time, so students don't worry. We will finish. No, this is not a good table. So let me just make it a little bit better. Okay, now, if here we say that this is the concentration of the hydroxyl ion, and this is the concentration of the hydronium ion. If we keep it like that, then I say 10, I want to see 10 to power 0. Let me just write them like that. I'll make, I'll adjust them so that they can become powers. 10 to power 1, 10, this should be negative, sorry. -1, 10 to power -2, 10 to power -3, 10 to power -4, 10 to power -5, 10 to power -6, 10 to power -7, sorry, 7, 10 to the power negative 8, 10 to the power negative 9. Will they fit? 10 to the power negative 10, 10 to the power negative 11, 10 to the power negative 12, 10 to the power negative 13. Let me add one more column here to my table. Or where is insert? For giving me the option, let me just select any of these and ask it to insert. Why is it not inserting?
Excuse me, sir.
Yes.
The option to insert is there.
Where?
Just
That's what I'm looking for actually.
yeah, just
It's
click
down
again.
there.
Yeah,
Where?
yeah, and then like on the place for the font and everything, just to the right. Just go down to the right.
All
No,
right.
to the
At
down, down, like where the font is, where it says like Arial body. The font
Bottom down,
says,
like
and
bottom
then
right.
go,
Oh,
and
where
then
is
go
that?
right, go right,
Oh,
go right.
yes. Ah,
Yeah.
wonderful, wonderful. Like that. Oh, thank you. That's the importance of having brilliant students in class. So let me put that. And then 10 to the power minus 14. So if now I can put this one to power 0 superscript 10 to power minus 1, also superscript 10 to power minus 2. I think there's no way of selecting all the powers, so I have to do one by one. But at least for the next column, I will not have to do this. I'll just copy and paste.
You can use format painter.
I do what?
Format painter.
I format window.
Format painter to apply the superscript to all powers.
How do I do that? Come again.
You highlight the power first, then go to format painter on the home tab.
Here.
No, the home tab, under home tab, where we have copy paste.
Oh, where we have copy paste.
On the ribbon, yeah.
Which ribbon is that? Which ribbon? Is it new?
Under the home tab.
Under the?
Sir, he's telling you where we have the paste.
Yeah.
Yes. Just
Yeah.
here below, there's something written format painter.
Here.
No, on the side. Up. Yeah,
Up,
that
yeah.
one. Format
This
painter.
one. Yeah, so what do
Yeah,
I do to that?
Click 2 times. First, highlight the power, one of the powers that you've already done.
I like the one that I've already done.
Yeah.
Like this one here. That one.
Yes. Then click the format painter 2 times.
I
Then
have
now,
done that.
go to the others now and apply. You highlight, then click one by one. Yeah. You
So
highlight, then click. Yeah, click. Not all of them. Just highlight the power. Then click.
The power here.
Yeah. Then
And-
go by one by one.
So I go one by one now.
Yeah.
That's brilliant. Eh? This one does not seem to. Yeah. So I click again. This one does not seem. Well, let me just do the traditional way. Because in the next few minutes, I'll be done. Eh? This is not a long lecture. And because it is also the last lecture, is there arm if we extend by 10 minutes?
It's okay.
You people have already tested a very good quiz, isn't it? And you must have seen the results, haven't you?
No, some of us can't see them.
Where?
Is there any student who has already seen?
Yes.
Yes.
Some
So why have others not seen?
we're in Z.
I marked the two classes.
Even some of the people in Y we didn't receive our grades.
Huh?
Even
Don't have
people
any
in Y.
Why?
Not all of us have the grades.
Why? I've marked everything.
We don't know.
Okay, let me explain. So if this is a 2 power 0, then this must be 2 power negative 14. So here that has to be 2 power negative 14. Then this one is 2 power negative 13. This one is 2 power negative 12. This one is 2 power negative 11. This one is 2 power negative 10. This one is 2 power negative 9. This one is 2 power negative 8. This one is 2 power negative 7. You can see now they are neutral. This one is supposed to be 2 power negative 6. This one is 2 power negative 5. This is power negative 4. This one is 2 power negative 3. This one is 2 power negative 2. This one is 2 power negative 1. And this one is 2 power negative 0. So there is a question that was asked. I'll answer that question from this. So could you kindly ask the question again?
I was asking
Yes.
for an acid, since they're saying it's more than -7, does it
Yes.
mean like -7, -6? Because that's how, because the powers are in negative form, Ama.
Now, when you see, we are starting, we are looking at this neutral situation here, isn't it?
Yes.
In this neutral situation, I'm trying to highlight it. In that neutral situation, the question now is, in which direction is it increasing and in which direction is it decreasing? When you go in this direction up here, I want to draw something here. When you go in that direction, the concentration of the acid is decreasing. And when you go in this direction here, the concentration of the acid is increasing. Is that one confusing anyone?
Yes.
Why?
Both the subscripts. Are
Yes.
they increasing or decreasing?
Okay, let me explain. This one, no, where is that? Let me do away with the. Let me do away with this. Now look at this one here. You know, this is the same as for purposes of explaining. This is the same as 0.00000. How many zeros are those? So 1, 2, 3, 4, 5, 0, 1. Okay? 10 to power minus 7 is the same as that. Is that okay?
Yes.
Yeah.
Yes.
Now, down here, just for you to understand, down here, what you have is the same as, let me put brackets so that doesn't confuse you. This is the same as 0.00. Now the zeros have decreased. That's the same as that. Can you see?
Yes.
So if you compare these two numbers, which one is bigger?
10 power negative 6.
10 to power negative 6 is bigger. Okay?
Yes.
Then down here, you have, let me put my bracket. Now we are reducing 2 zeros like that. So this is to mean that this direction here is increase in concentration. Okay? Can you see that?
Yes, but
And this is decrease in concentration. Somebody says, but can I clarify that? There are two students who have raised their hands. Yes, Asna, let us start with Asna.
Oh, sorry, sir. I forgot to lower my hand.
Okay, Anastasia.
Asking, does that mean that now from 10 to power negative 14, the acid is less concentrated, and as you move down to 10 power negative 8, it's more concentrated, and then at 10 power negative 7, it becomes neutral. Okay.
Yeah, okay, let me explain. We are looking at the combination of the acid and the base here. Okay? Now here, here, the concentration of the base is 1 molar. Because 10 to power 0 is what? Is 1. While the concentration of the acid here is very small, very small. 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That is the concentration of the acid. So, so this is very high, and this is very low. Okay?
Yes.
Here, they are equal. They are equal. Also here we write what? Equal. Here, it is very low now. Let me just copy this. Here we can say very low. Very low. While on the other side, that of the acid is very high. Very high. So as the concentration of one increases, the concentration of the other must decrease so that the product of the two concentrations is 10 to power minus 14. Any other question?
No, thank you.
So can we continue? Is it understood now?
Yes. Yeah.
Okay, thank you. So I go to the next slide. Sorry. So we are told rank the following solutions from most acidic to most basic. Now, if you look at these are 5 hydronium ions and 5 hydroxyl ions. What do we say? The concentration of the two is equal, and therefore that must be a neutral solution. Is it agreeable?
Yes.
Yes.
In part B, we have 7 of the hydronium, we have 7 acids versus 3 bases. So which one is higher?
Hydronium ion.
The hydronium, and you know this is the acid, isn't it? So it
Yes.
means that that solution is going to be acidic. In part C, we have 3 acids and 7 bases. So overall, it's going to be basic. So if you were to rank them in the order of increasing basicity, so most acid to most basic. So the one that is most acidic is B, then followed by A. Then the least acidic is C, which is the most basic. Is that okay?
Yes.
Good. Now, let me wake you up by taking the attendance. Let me refresh my browser so that I can reach the courses. So we are going to the attendance. Let me start with Z today. So attendance, we start with Anita.
Present.
Nicholas.
Present.
Obwog Denver. Denver.
Excuse me, sir, he's present. Yeah.
Okay.
Present, I'm here.
Okay. Edosa.
Present.
Isabella Gardner.
Present.
Lillian Gishego.
Present.
Amin Hassan.
Present.
Hasna Hassan.
Present.
Maria Janowala.
Present.
Edin Kisoka. Eldin. Is Kisoka in?
Present.
So I'm actually not able to mark here and at the same time read the charts because I can see the charts are flowing. So I'm not able to do that at the same time. So just agree that I call your name out. Michelle Mogusu.
I'm present.
Is that Michelle?
No, that was Eldin Kisoka, but I'm present, sir.
Okay, I have already marked Kisoka. Joy Mushemi.
Present.
Anastasia Munjuri.
Present.
Philip Mutinda.
Present.
Alice Odiwar.
Present.
Maria Patience.
Present, sir.
Kush Rana.
Present.
Sebata.
Present.
Grace Tuku,
Present.
Doreen Wainaina,
Present.
Njoki Waweru,
Present.
okay. Being that's all for Z. Any student that have not called out in Z?
Excuse me, sir.
Yes.
I'm not sure whether you heard me. Only my mic had issues.
Your name is?
Eldin Kisoka.
I marked you in.
Oh, sure. Thank you.
Okay. So we go to Y. And we begin with the Mustaf Abdinor.
Yes, sir.
Alice Alang.
Present.
Aneg.
Present.
Bilin. Daniel.
Yes, present.
Samuel.
Present.
Leju.
Present.
Lillian. Kempabazi.
She was in class. I don't know whether. Yeah.
I'm present.
Okay. Lucy Lojore.
Present.
Isaac Makuku.
Present.
Ivy Moshere.
Present.
Prince Moses.
Present.
Pardon?
Present.
Grace Mugambi.
Present.
There is somebody who is making some noise in the background. Angela Murithi.
Present.
Mary Murunga. Mary.
Present.
Michelle.
Present.
Prudence Diritu.
Present.
Charity Njuguna.
Present.
Barbara Omenya.
Present.
Yesh Patel.
Present.
Cecilia Selempo.
Present.
Umuhonza.
Individual or just
Present.
one person to submit for the group.
I would appreciate every person.
Lucy Wainaina.
Present.
Naiguran Winnie.
Present.
Okay, thank you. So we go back to our lecture. You can see we have 30 minutes remaining. But what is remaining is just to demonstrate how you can determine the pitch of a solution. So we should be able to cover that in the remaining time. So here we are looking at the pitch of a solution. Now, the pitch of a solution is given by the negative logarithm to base 10 of the concentration of the hydronium ion. And that is what is shown here. You can see pH is equal to the negative logarithm to base 10. You know, this base 10 is not shown in this formula here. Actually, a logarithm to base 10, we call it common logarithm, and common logarithms, we rarely show the base. But it is also good that you show the base in your calculations. But if it is common logarithm, it is always to base 10. We may not show, but know that in this particular equation, we have negative logarithm to base 10 of the concentration of the hydronium ion. And we are seeing that, note that the number of places after the decimal point in the pH equals the number of significant figures reported in the hydronium concentration. And let us see here. Now, the pH values for different solutions. In a neutral solution, you remember we said that the concentration of the hydroxide ion is equal to the concentration of the hydroxyl ion equal to 10 to the power minus 7. So where is this one coming from? This is coming from the, you see, pH is equal to negative logarithm to base 10 of the concentration of the hydronium ion, like that. Now, in a neutral solution, what is the concentration of the hydronium ion? The concentration is 10 to the power minus 7. I think we have said that. So we say that this is equal to negative log. Let me change the pen here. Negative log to base 10 of 10 to the power negative 7. Now, what do we know about powers in logarithms? This power here in logarithms can become a coefficient. So it can come here. That's why this one can be written as equal to negative into brackets negative 7. Where is this negative 7 coming from? The power which we have made a coefficient. So negative into negative 7, the logarithm of 10 to base 10. What is the logarithm of a number to the same base?
1.
1. So that means the whole of this one I'm circling here, gives us 1. And therefore, we now have negative into, this one is not being seen. Let me change the pen for better. So this is negative into negative 7 multiplied by 1. And this is where we are getting 7 from. Can you see that?
Yes.
What is happening? Are those students talking to me, or it is some other different discussions?
After this, formula of the pH, which is equal to negative.
Remember, the lecture is recorded. What is happening? Can that student please mute himself or herself? Now, let us go back to the very table. There's a table I had shown, and we pick any value. Look at this table here.
Excuse me, Prof.
Yes.
Can you go back to the slide where you were showing the formula of the pH?
I can't hear well. I think there's some background noise from one of the participants.
I'm sorry, it's my.
Can I know the student so that I can mute him or her?
Excuse me, it's my background noise. I'm so sorry.
It is your background, eh?
Yeah.
And you are the same person asking the question?
Yeah.
Yes, ask your question then.
On the slide where you're showing the formula for calculating the pH.
Yes, here. I have done away with the calculations. Ask your question, I'll answer.
Yeah, after you've written the formula for calculating the pH, the calculations you did.
Yes.
I didn't get anything. Can you repeat the thing, the example you used?
Okay. So look, we are saying pH is equal to negative logarithm to base 10 of the concentration of the hydronium. Are we together up to this?
Yeah.
Then we say that in a neutral solution, the concentration of the hydronium ion is equal to 10 to the power negative 7. You remember that?
Yes.
So that is why we are now saying this is equal to negative logarithm to base 10. And now instead of putting the concentration of the hydronium, which we know in a neutral solution is 10 to the power negative 7, that's what we put here, 10 to the power negative 7. Is it clear also?
Yes.
So it is at this point when I said that this negative 7, because it is a power, it can become a coefficient here. And that's why we are writing this is equal to negative into brackets negative 7, then logarithm. After taking the coefficient, you remain with this 10. So you have 10 to base 10. And I went ahead and said that when you have a logarithm to the same base, the whole of this term here is going to give us 1. Is it agreeable?
Yeah. Yes.
So the answer now becomes this one here, which is equal to 7. Have I answered your question?
Yeah, thank you.
Okay. And then I said we can go to the table here. We pick any value. We can pick any value for OH or any value for the hydronium. Which value do you want us to pick so that we can calculate the pH? Any value, whether it is a value for the hydronium or a value for the hydroxyl ion. Pick any value.
10
10 to
power
power negative 10.
2.
10 to the power negative
Maybe 2.
2. For the
Yeah.
hydroxyl or for the hydronium?
For hydronium, yeah.
For the hydronium. So
Yeah.
you have chosen this value.
Yes.
Okay. So we can say that, let me just add a slide here and do that calculation. So you have said that we take the hydronium concentration. You pardon by my bad scribings. This is equal to 10 to the power minus 2. Is that okay?
Yes.
Then we say now pH is equal to negative logarithm to base 10 of 10 to the power negative 2. This is equal to negative into brackets negative 2. Can you see where the negative 2 is coming from? Then logarithm of 10 to base 10. And we say that the logarithm of a number to the same base is 1. Therefore, the answer is coming from here. So what is the pH?
2.
The pH is 2. So interestingly, let me take you back to this. You know, we have calculated the pH from this value, the value that I have highlighted here. Can you see that? Can you see this value I've highlighted here?
Yes.
So supposing that we use this value, look, because the corresponding value for the hydroxyl ion is 10 to the power minus 12. Supposing that we use that value, are we going to get the same pH? The answer is yes. So will you allow me demonstrate?
Yes, please.
Yes, please.
Now we'll do this. Here we have seen that the concentration of the hydroxyl ion is equal to 10 to the power negative 12. That is what you saw from the table, isn't it?
Yes.
Now, there are two ways of calculating pH from this, and I'm going to demonstrate the two methods. Number one, calculate what we call POH. POH, which is equal to the negative log to base 10 of the concentration of OH. Remember, when we say pH, here we are putting H. But when we say POH, here we are putting what? OH. Can you see that? Then this is equal to negative logarithm to base 10 of 10 to the power negative 2. So we take this negative 12, sorry, negative 12, not negative 2. We take this negative 12 and make it a coefficient here. Then we get this is equal to negative into negative 12. Then logarithm of 10 to base 10. Again, the logarithm of a number to the same base, we say is equal to 1. So the whole of this gives us what? Gives us 1. And the answer that we are getting here is 12. Now, what we are getting is not pH, it is POH. Then we go ahead and say this relationship here, pH plus POH is always equal to 14. So if we have POH, can we get pH? That's why we say now pH is equal to 14 minus POH, which is equal to 14 minus 12. And the answer is 2. Did we get a pH of 2 in the previous calculation?
Yes.
Yes.
That's how you do it. So the other way of calculating the pH when you are given the concentration of the OH is, can I do away with these writings? Yes, Patience, ask your question.
Yeah, we said that pH is the negative logarithm of the concentration. So, and
Ask
also
again, ask again because I think you're breaking.
Yeah, we said that. Are you getting me now?
Yes.
We said that pH is the negative logarithm of the concentration of the concentration, and here also I'm seeing that POH is the negative logarithm. So they are the same in actual.
They are the same. What you put here is what comes here.
Okay.
Okay.
So there is no p hydrogenium, as in you cannot calculate the pH or POH of hydrogenium ion.
You are given the concentration of the hydroxyl ion, which is this.
Yeah.
So one of the things is that you can calculate the POH, which we have done and gotten 12. Then you use this relationship here.
Okay.
The other method, which I was going to show, is Look, we know that when you have the hydroxonium here, and you multiply by hydroxyl, can you see that? Is always equal to 10 to power minus 14. We have talked about this before. Okay. Students, have you gone?
Okay.
Now we are given that this is 10 to power negative 12, isn't it? So what do we do to get the concentration of the hydronium? We simply say that the concentration of the hydronium ion here is equal to 10 to power negative 14 all over 10 to power negative 12. And this one is going to give us 10 to power negative 2. Now, this one you can use to calculate the pH, because now this is the concentration of what? The hydronium ion. Is it clear?
Yes.
Okay. So let me go to, we were explaining which one now? We were here. I've done a calculation. So look at this example here. A sample of orange juice has hydronium ion concentration of 2.9 times 10. Yes, Nicholas, you have raised your hand.
Yes, but you didn't show us the second way of calculating it. Or like, is that what you just
It is
did?
the one that I've just shown.
Okay, thank you.
When you are given the concentration of the hydroxyl ion, you can use the relationship of the ion product equal to -10 to power negative 14 to calculate the concentration of the hydronium ion from there. Then once you have the concentration of the hydronium ion, you go ahead and calculate the pH directly. That's actually what I was explaining. So then can we look at this example? Yes, Angela.
Okay, so I just wanted to clarify on one thing.
Yes.
So basically you can't find the pH directly using the hydroxyl ion. You can only find it directly using the hydronium ion. Is that
correct?
Okay. Thank you.
Yeah. So a sample of orange juice has a hydronium ion concentration of 2.9 times 10 to the power negative 4 molar. What is the pH? And is the solution acidic? This is exactly what is being explained here. pH is equal to the negative logarithm of the hydronium ion concentration. So you substitute here, and that is what you are getting. So when you have a pH of 3.54, is this an acidic solution or a basic solution?
Acidic.
It's acidic.
Because it is less than 7, isn't it?
Yeah.
Okay. So look at this. The pH of a solution of non-hydroxide can be determined simply from the pOH. This one I have explained. A measure of the hydroxyl ion concentration is similar to the pH. That's why I said pOH is equal to the logarithm of the concentration of OH. You remember I did this. Then once you get that one, you use this relationship. Then you say that pH is equal to 14 minus pOH. The alternative is where you have this concentration of the hydroxyl ion and you take 10 to the power minus 14 divide by that particular concentration, so that you can get the concentration of the hydronium ion. And once you do that, then you can calculate your pH directly. Yes, Anastasia.
I have not understood how you have calculated that example.
Which one? This
The
one
one
here.
on slide 51. Slide 51.
This one.
Yeah.
Mm-hmm.
Please explain the calculation.
So can I do a calculation, the calculation myself?
Yeah.
Very good. Let me do this. So you are given that the concentration of the hydronium ion H30 plus is equal to 2.9 times 10 to the power negative 4. 2.9 times 10 to the power negative 4. Those with calculators, is it negative 4? Just for purposes of confirming. Yes, no, calculators, just have them ready so that I can guide you on how to work out this. Then we say now pH is equal to negative log to base 10 of the concentration of what? H3O. I hope we are following. So this is equal to, now we substitute negative log to base 10 of 2.9 times 10 to the power negative 4. Let me put a bracket. This is where I want to explain. Now, what you have here is a multiplication. This is a multiplication. Now, multiplication means addition. So you can write this one as equal to negative log to base 10 of 2.9 plus negative log to base 10 of 10 to the power negative 4. Any questions so far?
No.
So you can directly get the logarithm of 2.9. And remember, it is a negative logarithm. You can get this answer. All right. And you know this answer will give you what? What is this one going to give you?
4.
4. Huh? So those with calculators, what is the negative logarithm of 2.9?
Negative 0.4624.
Negative 0.4624.
4624. I'm not sure.
4624. Let me put negative 0.46. So plus what? This one gives you what?
4.
4. So what is 4 minus 0.46?
3.5.
Should be 3.5 something.
Yeah.
What is it?
3.537.
Yeah, 3.54.
Yeah.
Is that what we are getting?
Yes.
So that is the answer we are getting here. 3.54. So that is how they arrived at the answer. Is it understood?
Yes, thank you.
Any other question? Okay, so I explained that this one can also be obtained. The pH of a human arterial blood, you know, you are pharmacists now. You need to understand this. The pH of human arterial blood is 7.4. What is the hydronium concentration? Now, you move from the logarithm to the anti-logarithm. Because we are saying that pH is equal to negative log to base 10 of the concentration of the hydronium ion. Okay? But now if you are given now the pH is 7.4, you are given this is 7.4. How will you get this? You get the anti-log. So in short, you are sorry, you have this is equal to there's some noise somewhere. This is equal to negative log of to base 10 of the concentration of the hydronium ion. So you can multiply both sides by negative so that here it is negative what? This is negative 7.4 and this negative goes, right? So that now you can get the anti-log, meaning that you are taking out 10 to power negative 7.4, and that is going to give you the concentration of the hydronium ion directly. Is it clear?
Yes.
Okay. So you can see we just look at the interconversions. This slide here is showing you the interconversions. When you have the hydroxonium ion and you want to get the hydroxyl ion, you take 10 power minus 14 divided by what you are given. And if you want to move in the opposite direction, you just divide by what you are given. Can you see this? So if you are given one and you need the concentration of the other, you just take 10 to power minus 14 and you divide by what you are given. Then when you have the concentration of the hydronium ion, you calculate the pH by taking negative logarithm to that particular concentration. And when you have the pH and you want to get the concentration, you take 10 to power negative of that pH. The same thing applies here. When you are moving from a POH to the concentration, you take 10 to power negative of the POH. And when you are calculating pH and the POH, it is 10, it is 14 minus POH or 14 minus pH, the way I had explained. Is it clear?
Yes.
Yes, there are two students who have raised their hands. There is a Samuel. Samuel, ask your question.
Yes, please. May you explain again the antilog?
The anti-logarithm.
Yes.
Okay. Let me open this slide and explain the anti-logarithm here in the next few minutes. So look, if you are given pH is equal, for example, to 4.6, then somebody asks you to get the concentration of the hydronium. We say that pH is equal to negative log to base 10 of the concentration of the hydronium ion. like that. We are together, Samuel?
Yes.
So if you are given now 4.6 is equal to negative log to base 10 of the concentration of what? The hydronium ion, like that. I said you can do away with the negative here by multiplying by both sides by negative, so that you now have negative 4.6. Negative 4.6 is equal to log to base 10 of what? The concentration of hydronium ion. Are we together there?
Yes.
Now let me say something different. When you are there, from your mathematics, what is the logarithm? Logarithm to base 10 of 10. What is it?
It will be 1.
1.
Equal to 1, isn't it?
Yeah.
Yes.
What is logarithm to base 10 of 100?
It will be
2.
This is what?
2.
2. What is logarithm to base 10 of 1,000?
3.
3.
This is equal to 3.
3.
What is logarithm to base 10 of 10,000?
4. Oh.
This is equal to what? 4.
4.
We are together.
Yeah.
So this means if you take this base, can you see this base? Can you see what I have circled?
Yes.
And you raise it to this power. Then this becomes your answer. Remember your relationship?
Yes.
If you take this 10 here and you raise to power 2, you get 100. Hello?
Hello, yes.
If you take 10 here and raise it to power 3, you get 1,000.
Yeah.
Yes.
Similarly, if you take 10 here and you raise it to power 4, you get 10,000.
Yes.
Yes.
That means if you take this 10 here and raise it to a power of negative 4.6, it should give you what?
Concentration of
The
hydronium
concentration of the hydronium. Is it clear?
Yes.
Yes. So Samuel, I hope, was it Samuel who had asked?
Yes, yes.
Yeah, I hope it is clear to you also.
Yeah, it is clear.
So thank you. I think that's all for today. Any other questions?
About the grades.
Yes.
Group Z, we don't have our grades.
Not even a single student?
No.
Group Z, are you saying all of you do not have access to?
Yes, so we don't have.
Yes.
What about group Y?
Some in group Y and I also can't see
Why?
anything.
Why? Because it is new marked board groups, and I only hid the grids when I was marking. Okay, then let me ask my colleague whether there is something we are supposed to do for you to be able to see them. But everything is there. The marking scheme is also there. Okay.
Okay.
If there are further clarifications, please get in touch with me. I gave you my contacts yesterday. Is that okay?
Yes.
Thank you.
Yes.
So thank you very much, students. I want to wish you a lot of success in your end of semester examinations. In case of anything, we can continue to engage the platform. You can also reach me.
Thank you, sir.
So thank you. Thank you. Bye.
Thank you so much.
Bye-bye.
Bye. Yes,
Someone has a
Nicholas, you have your hand up. Nicholas.
Yes, Prof. Please, some people actually were complaining that the last question that we've taken the pictures, like they've not gotten their grade for that. I want to know whether you've been able to mark all of them.
Which question are you talking about?
The geometry, like the shape.
Uh-huh.
Now you've sent the pictures via
They are saying
Gmail.
what?
Yeah, like they've not gotten the grade for that.
They have not gotten.
Yeah.
There is a grade. There is a grade for each of the students who send their pictures. It is only a few did not send, and there's a comment that no attachment seen. So for every student who sent theirs, I was able to mark and grade.
Okay. Thank
Yes.
you.
Oh, yes. Yes, there are two more hands raised.
Yes, Prof.
Abdinor, yes.
Yeah, I can only see the mark that I got, but when I click on the question, it does not show like which question I got wrong and even the marking scheme.
You're in which group?
Group Y.
Group Y.
Yeah.
Okay. Let me ask my colleague whether there are some settings we have to change for you to be able to see everything.
Okay.
Yes. Any other student with a question? Okay, bye students. Then you can leave.
Bye, sir.
Bye, sir.
Okay, bye.
Bye, Prof.
Bye, Prof.